Hello, and welcome to AI for Mechanical Engineering. So far, we've looked at how we can define and formulate an optimization problem. In today's lecture, we'll be looking at how to actually solve these optimization problems. Let's now start with a one-dimensional case. So assuming we have a one-dimensional optimization problem, our goal was to find the value of x such that minimizes the value of f of x. So if we formally write this, our goal is to find the value of x such that minimizes f of x. And here, since we're considering an unconstrained case, we simply have to find the value of x that satisfies this condition. Now, in order to find the minimum point here, we can look at the derivative of the function denoted as f prime of x. So the derivative at any point along the function will give us information on the slope of the function. So in order to find the point that is minimum along this function, we simply have to look for the point at which the slope or the derivative of that function is equal to 0. Now for a convex problem, this value that we found, the local minimum, can be considered as, or can be seen as, the global minimum of that function. Now this is a one-dimensional case, and if we extend this example to a multi-dimensional case, let's say our x is a vector defined in an n-dimensional space. In this case, we'll be calling our function multivariate, and instead of looking for the derivative, we'll be looking at the gradient. So this is how we express a gradient, and the gradient, by definition, is an n-dimensional vector containing the partial derivatives with respect to each dimension. So for example, if we have n dimensions, we will be taking the partial derivative with respect to each dimension all the way up to xn. So if we borrow the same concept over from the one-dimensional case, for a multivariate optimization problem, our goal is to find the point at which the gradient is equal to 0. With this in mind, let's take a look at an actual optimization problem. So in the first case, we'll be looking at a problem in which we can find the direct solution by analytically computing the optimal solution. And again, we can do this by finding the point at which the gradient is equal to 0. Let's assume that this is our given function, and if we take the partial derivative with respect to each dimension, we first have this, and this. And if we represent this in matrix form, we can write out the set of linear equations as the following. And in order to find the optimal solution, we simply have to multiply both sides with the inverse of this matrix, which gives us our solution 1, 2. Now, one thing I'd like to note here is that we can express this function in terms of a quadratic form. So here we have something called a quadratic form. And the idea is that we can express this function in terms of vectors and matrices. Now, I'll be talking about this in detail shortly, but please keep in mind that this representation will come in handy later on, since we'll be mostly dealing with multivariate cases throughout this course. Alright, so here's a table that we can refer to when we're looking at the derivatives of matrices. Now again, this is our gradient. And if we solve for the gradient of AX, we end up with A transpose. Now if we assume that A is equal to 3, 2, and X is X1, X2, AX becomes 3x1 plus 2x2. And if we solve for the partial derivatives in each case, we end up with 3, 2, which is essentially equal to A transpose. Similarly, if we try this out for the second case, where X transpose A, where the goal is to solve for the gradient of X transpose A, we end up with A. The next case is where we have x transpose multiplied with x. And if we solve for the gradient in this case, we end up with 2x. By now, you'll probably see some analogy between the scalar case, where if we have some constant multiplied by x, if we solve for the derivative in this case, we end up with the constant in front of that variable. And if we have x squared, the derivative in this case is 2x. Now the last case is where we have a quadratic form, which essentially means that we have a matrix in between x transposed and x. If we solve for the gradient of this case, we end up with the following. And in a special case where A is symmetrical, in other words, A is equal to A transpose, you'll notice that we end up with 2ax. So again, if we draw the analogy between a scalar case, you'll notice that the final case can be seen as taking the derivative of ax squared, which in turn gives us 2ax. Now again, this representation is only valid if this is true, implying that A is symmetric. Alright, so with this table in mind, we'll be revisiting the example that we've seen in the previous slide. So here we have our table that we've defined, and this time I'll be representing this function in quadratic form. So here we have f of x is equal to x transposed. Here, because we do not have any constant terms, the final term is equal to 0. And if we write out the rest, we have the following. And this becomes our H matrix, and this becomes our B transpose. And because we know what the gradients look like according to this table, we can directly obtain the gradient. So using this part, we can represent the gradient of f as and for the second case, we can refer to this case where the gradient simply becomes. And here, because h is symmetrical, we can write out the following. Now if we substitute the values, 2h is equal to 4112 is equal to b. And just like we did for the previous case, if we solve for the values of x1 and x2 by multiplying both sides with the inverse of this matrix, you'll notice that we end up with the same answer. So this is another way to find the optimal value analytically by using the quadratic form of the objective function. Now let's take a look at a couple other examples. So first of all, we have something called an affine function, which is something that looks like a linear function, except that we have this bias term at the end, implying that the function is not actually linear. In this case, because we have a constant term, if we take the gradient of this part, according to the table, we end up with a. And if we compute the gradient a second time, because we have a constant, we end up with 0. Now in the second case where we have a quadratic function, which is the form that we've seen in the previous example, because we know what the gradient of this first term is according to this part of the table, assuming that p is symmetric, we can write out 2px, and our second term, according to this part of the table, as q. And finally, because we have a constant term, this becomes 0. And similarly, if we take the gradient of this again, we end up with 2p transposed. But because p is symmetric, we can simply write out 2p. Now the final example is when we're looking at the norm. So because we're looking at the norm, please keep in mind that this is actually a scalar value. And you'll probably recognize this form from the overdetermined case in linear algebra. In order to solve for the gradient in this case, we first start off by expanding this equation. And if we look at each component by component, we can find the gradients of each value. Starting with the first term here, if we solve for the gradient according to the table, we end up with a transpose A. And because this and this are symmetric, we can simply write out A transpose A x. Next, for the second term, we know that from this part of the table, we can find the gradient of this part as, which essentially is equal to 2A transpose B, and thus we have all our values. Similarly, if we solve for the gradient a second time, we end up with the following value. Alright, so with these examples in mind, let's revisit the least square solution from linear algebra. Here, our goal was to minimize the following objective function, and based on what we've learned today, our goal becomes to find the point at which the gradient equals 0. So if we start out by writing out our objective function as the following, and solve for the gradient of each term independently. For the first term, we end up with these two terms, and for the second term, we end up with this. For the third term, we end up with this, and because the last term is not dependent on x, we can regard it as a constant. Now if we further simplify this and set this equation equal to 0, you'll notice that we end up with the same solution that we've found. So here is what we've previously seen in the linear algebra case, and this is what we've solved for by analytically computing the solution of this optimization problem. But the caveat here is that in most cases, we cannot analytically solve or directly solve for the solution of these optimization problems. Instead, we take a slightly different approach and iteratively or numerically solve for the solution of this optimization problem. So this approach is used in cases where we do not have an analytical solution. And the core motivation here is that the gradient is a representation of the direction for the steepest ascent of a given function. So in other words, in order to move towards the minimum point, we want to move away from the direction of the steepest ascent, meaning that we want to move in this direction. Here we repeat this process until we finally find the minimum point of that function, in other words, our solution. So again, because we're trying to move away from the direction of the steepest ascent, the update is done in the opposite direction of the gradient, which is why we have this minus sign in the update rule. So here, because the gradient is pointing in the direction of the steepest ascent, we're not going this way, but rather move this way until we reach this point over here. Similarly, in this case, the gradient is pointing in the steepest ascent direction, meaning that we want to move towards this direction until we meet the minimum point of that function. Now, if we visualize this process, we start by selecting some initial guess and repeat this update until we reach a potential solution for the optimization problem. Now, one thing that you might have noticed here is that the gradient is being scaled by some factor here, in which we denote as the step size. So this step size determines how big of an update we're making at each iteration. So for instance, if we have a small alpha value or step size, technically we would be able to find the optimal point, but we'll converge very slowly. On the other hand, if we have a large step size, it is very likely that we will overshoot, and in worst cases, we will diverge. We can also have a varying step size, where in this case, the step size decays through each iteration. Now this potentially allows us to find the optimal point relatively faster, yet with greater accuracy towards the end as we're taking smaller steps towards the end. Here, one thing I'd like to mention is that the selection of the step size is relative and greatly depends on the type of problem that we're solving. However, if we assume that we've selected an appropriate value for the step size, the next question is, at which point will we converge? In the examples that we've looked at so far, we've looked at convex optimization problems, meaning that the local minimum that we've found is guaranteed to be a global minimum due to the properties of a convex optimization problem. The bad news is, in reality, most of the problems that we'll be encountering are considered to be non-convex optimization problems, meaning that the points or the local minimum that we've found are not guaranteed to be global minimum. The good news, however, is that we can attempt to overcome this issue by randomly initializing the points and running the optimization multiple times. So for instance, if we randomly initialize the initial points at these locations, if we solve the optimization problem for all of these initial points, you can see we have multiple local minima, and by comparing each of these local minima that we've found, we can determine that this point is a better local minima than the point over here. Again, this still does not guarantee that we have found the global minimum. However, we can make a step towards finding a better local minimum. And just like we've done for our previous examples, let's consider a multi-dimensional case. So here, if we consider x to be a two-dimensional vector, if we visualize the objective function, we end up with a surface that looks like the following. So just like we did for the one-dimensional case, where we started off with an initial point and move towards the local minimum, here we select random initial points and iteratively move towards our local optimum. So taking this into account, if we look at the example of the high dimensional case, if we rewrite this gradient, you'll notice that the direction is no longer dependent on a single dimension. A more accurate representation for our case would be the following, where our goal would be to move away from the direction of steepest ascent, since our goal is typically considered to be finding the minimum point. Alright, so if we compare the two different ways that we've used to find the solution of an optimization problem, the first approach was to directly find the solution analytically, and the second case was to find the solution through gradient descent. Now again, gradient descent is easy to implement, and at a high level it is very general, meaning that it is applicable to many differentiable loss functions. Now gradient descent is a very powerful tool that provides a general learning framework and can be used for both classification and regression tasks. So later on in this course, we'll be training neural networks through gradient descent. And from an implementation standpoint, the good news is for many classes of optimization problems, people have already done the hard work of developing these numerical tools. Specifically, we have CVX or CVXPy, which is a module that we can use in Python, especially to solve convex optimization problems. However, in the context of deep learning or neural networks, we'll be using a module known as TensorFlow. So just as a quick preview of how we can train neural networks, a neural network is defined by something called weights, which are essentially the parameters of that model. And our goal is to find the best set of weights or parameters that is suitable for the task we're trying to solve. So just like we did for the gradient descent case, we start off with some initial guess, and through gradient descent, we attempt to find the set of weights that minimize our cost or loss function. And again, you don't have to worry about the implementation of this gradient descent algorithm because we'll be using TensorFlow for the training process. Now, if we look at one final example of how we can implement gradient descent, here we're trying to find the minimum of this objective function through gradient descent. Now, because this function is extremely simple, we already know that the analytical solution of this is 3 and 3. However, we'll be assuming that we do not know the analytical solution and we'll be solving the solution through gradient descent. So first of all, if we represent the given objective function in quadratic form, based on the table that we've previously looked at, we can find the gradients of each component, in which we can write out as the following. So in terms of implementation, we first define our H and G matrices and our step size as well. And for a given number of iterations, we define the gradients over here, multiply it with our step size, and update our new x based on our current x. If we repeat this process many times, we end up with a solution value that is very similar to the analytical solution that we've been able to determine earlier on. Alright, so today we've looked at two different ways to solve optimization problems. First, directly through analytical solutions, and second, through gradient descent. In the next lecture, I'll be looking at some examples of optimization problems. This is the end of today's lecture, and thank you.